Hello everyone, welcome to all of you. In the last lecture we have discussed about entropy, and I tell you entropy principle. What is entropy principle? And we have seen that in the last lecture ds is always greater than or equal to dq by t. Process is reversible or irreversible, and I told you that ds is always greater than dq by t. If we take a isolated system means a system in which there is no energy transfer, no mass transfer, then that system is called isolated system. It means dq is 0 in isolated system. In isolated system, then we have write this equation: ds is always greater than or equal to 0. This is the entropy principle. Entropy principle says that the entropic change of any isolated system is always greater than or equal to 0. If a process is reversible, then ds is equal to 0, and if a process are going to irreversible, then the entropy of isolated system is always greater than 0. Then how we can relate this? The entropy of universe is always increasing. That's mean isolated system is nothing. Isolated system, a best example of isolated system is the universe. Universe is considered as the isolated system. Universe, this is universe. A universe is treated as the isolated system. No one any isolated system, but universe is treated as the isolated system. That means here you can say this is the system, and outside the system is called surrounding. Then we take a whole thing. This is system and surrounding. This is become a universe. This is become a universe, and we have treated as a system. Then it become isolated system. Universe is the isolated system. If we say that isolated system entropy increases always, then we can also say that ds universe is always greater than or equal to 0. This is the entropy principle. The entropy principle says that the entropic change of a universe is always equal to or greater than 0. It's mean the change of entropy of a universe is always positive. Okay. If I say that the entropy of a universe is increasing, it means that is a universe delta S universe comprises two things, that is system and surrounding. This means the delta S system plus delta S surrounding, this thing. And entropy principle says that this is the greater than or equal to 0. If a process is going on reversible, then equal to 0, and if process are going on irreversible, then this is always greater than 0. It means always positive value gives delta S universe. These all things are discussed in the last lecture, and I told you that in the upcoming lecture I discussed the application of entropy principle. But before starting the application of entropy principle, I would like to give a better concept of entropy change, and how we calculate entropy change. And in the reversible process, there is a entropy change in reversible processes. Here discuss this thing, and then we are further moving on the application of entropy principle. This is the entropy change, how we calculate the entropy change in the reversible process. We know already that in a reversible process ds is equal to dq by t. We already, this is the proof. In the previous lecture we already proved that ds is equal to dq by t. And how it is applied in the numerical, how it is applied in the numerical to solve the entropy question. Then there are three concepts are used to calculate the entropy change. In the various problem we can see that there is three conditions to calculate the entropy change in the reversible processes. That is, first one is the thermal energy at a single temperature. A thermal energy is containing and a single temperature fixed. Then we calculate the entropy change. This is the first case. And there is the finite mass of solid or liquid. Then ask the question that how entropy change. And third is the ideal gas. Ideal gas is given, then calculating the entropy change. Now we move to calculate the thermal energy at the single temperature. In this case what happened, I explain it. Let's calculate how change in entropy in thermal energy at a single temperature. That is, there is two case here. A reservoir is given or phase change problem is given. Then how to calculate this thing? A reservoir means, what is, you understand a reservoir is that things which containing a capacity of large capacity, and it is the thermal energy reservoir. Then it having a large amount of thermal energy, that is, this is the reservoir. Suppose that this is reservoir and containing a large capacity of heat energy. Suppose this is the heat energy, large reservoir. Suppose you imagine that this is a furnace which containing a large amount of heat. This particular temperature are given, that is, temperature is given, suppose T is given 1600 degrees Celsius, and we provide heat to the reservoir. Suppose we provide heat, this heat Q is provided to this reservoir. Then what happened? There change in any temperature if I provide the heat to the reservoir? No, there is no change in any temperature, because this is a large capacity of heat. If I provide heat or reject heat, there is no change in temperature, because it's having a very large capacity. Suppose I explain an example. You can imagine that the water reservoir means you can imagine a sea or river. This is the river, and I tell you that you pull down a bucket water. Then what effect on this thing on the river? Any effect produced on the river? If you pulled out one bucket water, there is no effect, because this is a very small quantity and this is the large quantity. Then there is no effect on this river. Similarly, this is the large capacity of heat. If I provide the heat, then there is no effect on the reservoir, and this temperature is 16 degrees Celsius. Then its temperature is maintained at the 1600 degrees Celsius. I think you are understand what I am saying. This is the temperature is here fixed, not changing temperature. If I rejected heat, then also temperature is not changed. Temperature is maintaining 1600 degrees Celsius, because this is the large amount of heat and it containing a large infinite mass. If I provide heat, then this heat is distributed all particles, all masses. There is an infinite mass, and this heat is distributed to all particle, and there is no change in any temperature of this reservoir. So this is, and we ask that how entropy change of this reservoir. if any problem in given, this is the reservoir, this is reservoir A, and its temperature maintain, suppose 2600 Kelvin, 2600 Kelvin, and we provide some heat. This is the reservoir, this is the reservoir, and we provide some heat. Suppose the Q heat is added in this reservoir, Q is added in this reservoir. Then we ask you that how entropy change in this reservoir. So you know that this ds is equal to dq by t, and t is this temperature and dq is given. So then you calculate the entropy change of this reservoir. And how calculate? I solve this concept. Okay. Suppose a reservoir is given. That is reservoir A is given, and its temperature maintaining 2600 Kelvin. Then we provide some amount of heat in this reservoir. This is the reservoir A, and we provide heat. Then what happened? This heat is distributed to all the members, all the particles of this reservoir, and there is no change in any temperature of this reservoir, because this is a large amount of heat in this reservoir. A reservoir is that thing in which having a large capacity. If I provide heat, then there is no effect on this heat, and its temperature is maintaining 2600 Kelvin, then it's maintaining at 2600 Kelvin. This is a not changing in temperature, because this is the reservoir. If I reject heat, then also there is no effect on the any temperature on this thing. There is a temperature is fixed. So our calculation is the single fixed temperature reservoir, and this is the having an infinite mass, and this heat is distributed to all masses, and there is temperature is no change. So we applied the entropy change formula, that is a ds is equal to dq by t. This heat is suppose reversible, because we are interested to find out reversible heat transfer. We already said that the entropy change calculation is a reversible manner. Then we can write ds is equal to dq by t, and this temperature is the fixed. This is not changing. Means if we integrate this, t is outside of the integration. Let's see, ds is equal to dq by t. T is the constant, because this is a reservoir, there is no change in temperature. Then we integrate this ds, integrate this, t is outside of the integration, 1 by t. This is the dq. You already know the integration of dx is already said that this is the value giving x. So here ds means change in entropy. Entropy is equal to integration of dq is q upon t is the constant value, this is the t. Now this is the entropy change in entropy of this reservoir A. If heat is added, then it is taken positive, and heat is rejected, then this value is taken as the negative value. So this is the formula of Q by T for the reservoir. And any reservoir is given and heat is provided or rejected, then you calculate the entropy change of reservoir is that Q by T directly, because T is the not function of Q. T is the always fixed in the reservoir. Okay. In this case, we also take another example, that is the phase transformation. Phase transformation takes place only fixed temperature and fixed pressure, because here you can see here 0 degrees Celsius ice is converted into 0 degrees Celsius water. That means here temperature is fixed, temperature is not changing Kelvin. This is the solid, this is the solid, this is the solid, and it converted into the liquid. liquid state. Then we see here the phase change. In phase change, pressure and temperature are always constant. So I ask you, what is the entropy change in the phase transformation? That means that there is the heat. Heat is, in this heat is called latent heat. Latent heat. This is the heat is called latent heat. Latent heat. If I ask you what is the change of entropy change, then you can say that dq is equal to, ds is equal to dq by t, and this dq is latent heat. That means ds is equal to latent heat upon that temperature at which phase transformation occur. That means here temperature. This is. If I ask this problem, then you can say the entropy change is latent heat. This is a solid to liquid, means latent heat of fusion. If here liquid is converted into vapor, then we use the latent heat of vaporization, and the particular temperature, for example, atmospheric pressure 100 degrees Celsius water is converted into 100 degrees Celsius vapor. Then you calculate what is the entropy change in this process. You can simply say that the latent heat and T temperature, that means 100 plus 273. This is the value calculating, and this is called entropy change in the phase transformation. This is similar to the case of reservoir, because here also temperature is fixed and latent heat is not depending on this T. So you can write here entropy change in latent heat upon temperature. This concept is utilized in numerical when a reservoir is given or phase transformation problem is given. You simply apply the ds is latent heat upon T, Q by T. Okay. Second condition is given in the problem here: finite mass of solid and liquid. Suppose a body which having a finite mass. Suppose this is a solid body, and that its temperature is this time temperature is 300 Kelvin. Now we provided some heat provided here, suppose Q, heat provided. Then what happened? After some time the temperature of this body is increasing. Suppose this is a marker, and if I provide heat, then their temperature, this marker temperature is increases, because this is the finite mass. This is not a reservoir. So here temperature is increasing, and after some time its temperature become 900 Kelvin. Then what happened? I ask you, the heat is added at 300 Kelvin or 900 Kelvin. You have no answer. Why? Because it is not known that temperature is given 300 or 900 Kelvin. Because if we suppose here this is the mass, we provided heat, then this is the temperature 300 Kelvin. Now providing heat, then its temperature increasing. It become 400 Kelvin, and then further we provide heat, then its temperature also increasing 600 Kelvin. Then further we provided heat, then its temperature final 900 Kelvin. That means here we see that temperature is not constant. Temperature is always increasing with the providing heat. Heat is the function of here temperature. Heat is provided, then temperature increases. First this is the 300 Kelvin, then heat provided, then it increasing the temperature 900 Kelvin. Here temperature is not constant. In the previous case in the reservoir or phase change temperature is constant, but here temperature is always step by step increasing when we provided something heat. Now we how calculate the entropy change in this process, and now we calculate how entropy change in this thing. Suppose here 300 Kelvin, you see that 300 Kelvin and it's become 900 Kelvin. When a heat is provided, heat is not a particular temperature 300 Kelvin, it increases step by step, then it reach at the 900 Kelvin. So how calculate? We have already formula ds is equal to dq by T, because this is the reversible heat transfer. We already assumed that our calculation is based on the reversible heat transfer. Now we take a particular temperature here, that means here temperature T, and here we provided a small amount of dq. Then we can write ds is equal to dq by T, and here temperature is not constant, because when we integrate this, then temperature is not taken out from the integration. And you know that when any elemental body and provide dq, then we can write dq is equal to mc dt. M is the mass of body and C is the specific heat of body, and dt is the small change of the temperature. Suppose here particular temperature and its change in temperature is dt. So we can write here dq is equal to mc dt upon T. T is not taken out from the integration, because temperature is the changing when provided heat. Now we integrate this, then we can calculate the S2 minus S1. This is the entropy change of this process. Now integrate this 1 to 2. The MC is the constant, mass, M is the mass, C is the specific heat. Now here S2 minus S1, that is MC, this is outside, m2 dt upon T. You are already known that 1 by x dx, this integration is ln x, here temperature dt and T. So we can write here mc, here ln T, this is 1 to 2, mc ln T2 upon T1, S2 minus S1. This is applied when the finite mass is given, then entropy change formula is mc ln T2 upon T1. Here not applied the Q by T. Q by T applied only when temperature is fixed. When a reservoir is given or phase transformation is given in the problem, then we can write Q by T. But in this case, finite mass of solid or liquid, we apply the S2 minus S1 MC ln T2 upon T1. Here C is only one value in the solid or liquid. So for solid and liquid, specific heat is one value. In the gaseous state, there is the two specific value, constant heat, constant volume and constant pressure. But in the solid and liquid, only this heat capacity is the one value. So we can apply this formula, and here example you can solve. Then you can write mc ln, this is the T2 900 upon 300. You calculate this value, then you get the entropy change in this process. Okay. Now we see third case, ideal gas. How entropy calculation in the ideal gas? Ideal gas, you know, it is follow PV is equal to mRT. Here you see that the volume of gas is always variable. This is the not constant. If we increase pressure, then the volume is decreases, but mass is also constant. That means this is also case of the finite mass case. Previous one we discussed solid and liquid. Then there is the mass is the finite. This is the not infinite mass. So I applied the previous formula, that is the ds is equal to dq by t. dq by t, here temperature is the function of heat. Here this is the not reservoir, then temperature is not fixed because all values are variable. So we use here first law of thermodynamics. First law of thermodynamics says that for the reversible case, the dq is equal to, here you can write du plus p dv. I think you are study about the first law of thermodynamics, that is the dq is du plus p dv. You can write here ds is equal to dq value putting from this equation du plus p dv upon t. This is the generalized form of entropy change calculating in the ideal gas. You can expand this formula. You can also, for the ideal gas, du is written as Cv, mCv. If a mass is given, mCv dt, and you can write this value in this equation, then you get ds is equal to mCv dt plus p dv. In this side you can write t, p by t dv. You also calculate p by t value. Here you can see here p by t is equal to mr upon v. Here you can see p by t is equal to mr by v, and putting the value ds is equal to mcv dt upon t plus p by t mr dv upon v, here right. And if you integrate 1 to 2, process 1 to 2, yeah, this is a simple integration that you can get ds, that means s2 minus s1 is equal to mcv ln t2 upon t1. We already integrate in the previous case, and mr dv by v, here also dv by v you can write plus mr ln v2 upon v1. This equation is valid for the ideal gas entropy change. Here you can see that the Cv, this is there is two value of the specific heat in the gaseous form, because Cv is the constant volume specific heat, and you can write also R is equal to Cp minus Cv. Then putting this value you get in term of Cp. Cp is the specific heat at a constant pressure, and Cv is the specific heat at a constant value. So you get three equations from putting this value. This is the this proof is the homework for you. You put the this value and get another equation for S2 minus S1. I write directly S2. I rub this because there is no space. S2 minus S1 is equal to mCp ln T2 upon T1 minus mr ln P2 upon P1. We put R is equal to Cp minus Cv, then we get result this. You can practice this thing. S2 minus S1 is mCp ln V2 minus V1 plus mCv ln P2 upon P1. There is a three equation we get. In the problem, in any problem given condition, you apply the three equations. First equation, second equation, in the given condition. According to given condition, you apply three equation and learn these three equation entropy change for the ideal gas, because these equation are already asked in the GATE examination or SSC JEE examination 1 marks question. This is always asked in any engineering examination, competitive examination. So you learn this equation. So we have seen three types of condition in the reversible case, how to calculate entropy change. This is very helpful for the question solving in the entropy chapter. In first one case is that entropy change of a reservoir, and second one is that the finite mass body is given, and what is the entropy change we calculate MC ln T2 upon T1, and for ideal gas this three equation is applied for the entropy change. In the reversible this is only for the valid reversible case, not irreversible. All formulas are valid only for the reversible case. Okay. Now we are ready to discuss about entropy principle application. Its application is widely because this is the generalized theorem. Every process is going on the law of entropy principle, because any process is occur, that's mean that time the entropy of a universe is always increasing in any process. For any example, this is the heat transfer process is occur only when the entropy of a universe, that means the system entropy plus surrounding entropy is always greater than 0. Then the process is possible. If any condition the entropy of a universe is negative, then the process is not occur. There is only one thing that's possible, either process is reversible or irreversible. If process is irreversible, then the entropy of universe is always increasing, then the process is occur. Okay, actual process always this is the irreversible manner. So entropy of universe is always increasing. This is not negative. If this is negative, then any process is not possible. So this is the generalized process. It can applied anywhere. This comes from the second law of thermodynamics. That means you know already that entropy is coming from the second law of thermodynamics. So this is the called of second law of thermodynamics. Second law of thermodynamics is called directional law. Why directional law? It says that the process is possible only one direction. That means the entropy is increasing of a universe. Then the process is possible. Its reverse is not possible, because entropy of universe is negative, then the process is not happening. Only process is happening when the entropy of universe is increasing. So this is the called directional law of thermodynamics. That is the second law of thermodynamics, which is related to the entropy principle. Entropy principle says that the process is possible only if the entropy of universe is increasing. Now its application is C. The transfer of heat to finite temperature difference. Suppose any reservoir. This is the reservoir A. Reservoir A. This is what? This is the reservoir, and it is connected a rod. This is the rod, and another reservoir, that's it, B, and its temperature is T1 and its temperature is T2. And the process is that the heat transfer from A to B. This is, and here T1 is greater than T2. This is given. This is given. How entropy principle is applied here? And here heat is transferred in this direction Q. This is the heat direction in Q. We applied the concept of entropy principle. Let's see. The reservoir, for reservoir A, for reservoir A. What is change in entropy? I already explained. This is the reservoir, and heat transfer from the reservoir. It means this heat is rejected this reservoir, this is rejected the reservoir Q del S A. This is the reservoir entropy change in A T1. This is the T1. You understand, because T1 is the fixed, because this is the reservoir, then you directly Q by T T1, and this is a heat is rejected from the reservoir A, so this is the negative. And for reservoir B delta S B, this is heat is rejected to the reservoir B. That means heat is added to reservoir B and its temperature is given T2. T2 is always constant and T1 is always constant, because we take a reservoir A and reservoir B. Our assumption is that reservoir A and reservoir B, and heat is transferred to reservoir A to B, and we can write here the entropy change of reservoir B is Q by T2. And here there is no interaction of heat. There is no interaction of heat from the surrounding. There is no interaction. Heat is not transferred in the surrounding. Only this thing. Our assumption is that only temperature is temperature reservoir A temperature T1 and reservoir B temperature T2, and heat is transferred by this rod Q this reservoir B. There is no interaction of the environment or surrounding. Only that means the entropy of environment or surrounding is 0, because you know that the Q by T, here Q is not present in the surrounding, so here entropy of surrounding is 0, because Q is not rejected from in surrounding. And you can see here there is a system means system. This is a system A, system B. So what is the system? This system means a delta S system. That means the entropy change of A plus entropy change of B. This is the system. You know, entropy principle said that the entropy change of a universe is always greater than 0. That means the entropy change universe comprises system and surrounding. Here system is what? System is A and system is B. Both combined taken as a system, and surrounding entropy is 0, because there is no heat interaction between the surroundings. So here we take the delta S universe, that is this thing surrounding is the 0, and only we write here Q upon T1, that is a delta S is A, here Q1 by T1 plus Q by T2. Solve this Q here T2 T1 minus T2 upon T1. This is the result. That means we can write here the delta S universe is equal to Q T1 minus T2 upon T1 into T2. This is in this process heat transfer takes place in reservoir A to reservoir B. We get a result, the delta S universe is T1 minus T2 T1 into T2. This value is positive or negative? I ask you. This value is positive or negative? You can say here T1, we already discussed T1 is greater than T2. This is the condition we have taken. This is reservoir A and T1 is greater than T2, then heat transfer takes place. So we can see here this give positive value. Positive value means delta S universe always greater than 0. So this process takes place only if delta S universe is greater than 0. It means what? The entropy change of universe is greater than 0. That means this process is going on irreversible manner, because I say that the entropy change of universe is equal to 0 or greater than 0. If equal to 0, then process is reversible, and if greater than 0, then this is process is irreversible. Then we increase temperature difference, then delta S is increasing. That means irreversible process, irreversibility may be increases. So the temperature change increases, then irreversibility increases. In this problem we can prove that the delta S universe is always greater than 0. Next application is also available, but this video is very long, so in the upcoming lecture I discuss the next problem which is based on the entropy principle. I think this is enough for today's session, and I revise that what I have read today's session. That is, first one is that the entropy principle, and entropy principle and entropy change for the three conditions. This is the reservoir, this is which having an infinite mass and a finite mass condition. Also we study that is a solid or liquid and ideal gas. We prove that the three equation for the ideal gas, you must learn that three equation, because that directly asked in the various competitive examination. And then we see that the application of entropy principle for the finite temperature difference, that is the reservoir taken T1 and T2. If we T1 minus T2 increases, that means temperature difference is increases, that means entropy of universe is increases, that means more irreversibility present in this process. If I ask you, when a temperature difference increases, then you can say that the irreversibility is also increasing. You can prove that this thing. This is enough for today's session, and in the upcoming lecture we discuss about more and more application of entropy principle, and we discuss about also how to solve the questions of entropy which are asked in the GATE examination and another competitive examination. And you have any query related to entropy chapter, you can ask me in a comment box, or you contact my contact number. Okay, thank you.